All right, welcome everyone to the fourth and final video that we have here on chapter 12, talking about liquids and intermolecular forces. Right? So far, we've talked about physical states of molecules that exist, right? Solids, liquids, gases. Talked about the types of intermolecular forces that can exist and how we can try to determine what molecules have what type of intermolecular forces, right? And we've talked about the relative strength of those intermolecular forces, how that plays a role in the volatility, right, the vapor pressure of a molecule, and how that's related with boiling point, okay? And so here, talk about phase changes and phase diagrams to kind of talk about this one, right? Because we talked about boiling point, liquid to gas, phase change, right? But there's different types of phase changes that can occur, right? I can have a solid to a liquid, right? Melting, fusion, same thing, different name, right? Or liquid to a solid, freezing, right? You can have sublimation, right? Going from a solid to a gas, right? Carbon dioxide, right? Dry ice does that at room temperature, okay? You have vaporization, right? Liquid to a gas, condensation, gas to liquid, right? So there's a bunch of different types of, phase changes that can occur, okay? Here, the red lines are marked as endothermic processes, right? It takes energy to do this, right? It takes energy to go from a solid to a liquid or liquid to a gas, right? Because you're having to break up intermolecular forces that exist between molecules, right? And you're having to increase the kinetic energy in your system in order to try to get these things to break apart to eventually, say, go to the gas phase, right? And the blue lines represent exothermic processes, right? These things give off heat, give off energy, okay? Because you are essentially gaining a bunch of attractive interactions going from a gas to a liquid to a solid, right? And that's going to give off energy to the environment, so it's exothermic. Okay. Here we have a plot of right, different heat of fusion, vaporization, and sublimation, right? As a reminder, heat of fusion is going from a solid to a liquid, heat of vaporization is going from a liquid to a gas, and heat of sublimation is going from a solid to a gas, right? And we have these different heats for these different species, right? If we notice in each one of these things, right, notice here, for example, in butane, right, my heat of vaporization is 5 kcals per mole, or kilojoules per mole, and my heat of vaporization is 24 kilojoules per mole, and my heat of sublimation is 29 kilojoules per mole. And if you notice in each one of these things, right, that this enthalpy of sublimation, right, is equal to the enthalpy of fusion plus the enthalpy change related with vaporization, okay? Then each one of these things, you add the enthalpy of fusion and vaporization together, you'll get the enthalpy change related with sublimation. Okay? Right. So we'll finish up talking here about phase diagrams. Okay? So we just talked about these phase changes, right? Melting, vaporization, right? So these are labeled on your phase diagram, right? It's different phase changes we just talked about. Okay? Right, so in these typical type of phase diagrams here, right, we have our solid phase, our liquid phase, and our gas phase, okay? Right, these phases are separated by what are called phase boundaries. So these lines here, these are called our phase boundaries, okay? These phase boundaries, right, separate our different phases, right? And what occurs at these phase boundaries are these phase changes, these meltings, vaporizations, and so on, right? Our solid phases typically exist at very low temperatures and high pressures, right? Gas phases exist at very low pressures and high temperatures, right? And then liquid phases are somewhere in between, okay? Right, on these phase diagrams, there's what's called a triple point. The triple point is where all three phases exist in equilibrium with each other, okay? So at the triple point, you have gas phase, liquid phase, and the solid phase all existing and being stable at that point, okay? So, right, for example, right, at very high temperatures and low pressures, only gases are going to be stable, right, for your molecule, right? Okay, and then we also have out here what's called the critical point. Okay, the critical point here is labeled point C, is a point where your liquid phase no longer really exists, and you exist now as sort of a supercritical fluid that looks very similar to a gas phase system. Okay, so past the critical point, past that temperature of your critical point, you typically don't have a system that really looks like a liquid anymore, and it looks much more like a gas phase, but kind of a more condensed gas. So it's often called what's called a supercritical fluid. Okay. Water has the same type of phase diagram as other things, right? You have a triple point. Okay. You have your phase boundaries between your different phases, right? And you have your supercritical point, okay, or your critical point, right? One of the things to note about water that's different is that this line that separates the liquid and the solid, right, goes up and to the left, okay? Most species besides water, besides H2O, right, water, H2O, most species besides this, the solid liquid line goes up and to the right, and that's because, right, the solid liquid line is related with, right, it going up to the left is because the solid form of water, ice, is less dense than the liquid form, okay, right? And the properties of this, of water, is very, very important, okay, right? Why, say, during winter times, lake freezes over, but fish and other species can survive underneath that water during the winter, right? And they don't all die off, is because the fact that the ice, when it's formed, when water is freezing, forms on top, and then it forms this insulating layer on the top of the lake, right, that keeps the water below warmer than that freezing point, so that that water still exists, so the lake doesn't completely freeze over, right, in the course of the entire winter, right? This is why our oceans don't completely freeze over, things like that, right? Because you have this ice floating on the top instead of sinking to the bottom and then forming more ice and sinking to the bottom and forming more ice and sinking to the bottom, right? Life would not exist if water didn't have this property where ice was less dense. Okay. All right. And so, right, if we want to go between these phases, right, by increasing temperature, we have these things called heating curves, right, where what you do is you heat some solid, right, in the bottom of this heating curve, you start by heating your solid. You then reach the melting point and you melt that solid, right? You're adding an energy, right? As you go to the right here, we're adding an energy, okay? We're adding in heat, we're increasing the energy of the system. So that heat goes to increasing the temperature initially, then it goes to melting that solid. Then you're in the liquid phase, and now you're increasing the temperature of your liquid, and then eventually you've increased the temperature of your liquid enough to where the vapor pressure of that liquid equals the atmospheric pressure, and then you can vaporize that liquid and it forms the gas, and then you just start heating that gas as you keep on adding more and more energy and you're increasing its temperature, okay? So this is a typical heating curve. This is what it looks like for any species or any compound, okay? Right, notice that these phase changes occur at constant temperature, okay? So as you're adding in energy to your system, you're not increasing the temperature of that solid. Instead, you're breaking these intermolecular forces, right? You're separating these atoms and molecules, right? And it's causing this phase change, right? So phase changes, right? You add energy to your system, and it changes what phase you're in, but it does not change the temperature of that system. Okay? Just as a reminder, right, from 1341, this heat that's required to, right, the amount of heat that's required to change the temperature of some compound is related to this equation here, okay? Right, this equation Q equals NC delta T, right? N is number of moles, right? N equals moles, right? Delta T is your change in temperature, right? And then C is what's called your heat capacity. Okay, right? C here, your heat capacity. Okay, right? That's the amount of heat that's required to change the temperature of some substance in a solid, liquid, or gas phase, right? And to undergo a phase transition, the amount of heat that is released or required to undergo that phase transition, is related with the enthalpy change of that transition times n the number of moles. Okay? And so that will do it for chapter 12, and talking about intermolecular forces, right, and phases of your substances, right, solids, liquids, gas phases, right. Okay. And we'll do plenty of examples related with these concepts in class.